Hello everyone and welcome back to Science Why. Thank you for clicking on yet another video. I'm out and about in the car today. As you can see, it's quite a nice day to be out, but quite a bumpy road as I drove up that track there, guys, which got me thinking about the suspension on cars. How do they know whether the suspension is going to be strong enough to absorb the shock from the road? Let's look into it. Well, if we have a look underneath the back of the car here, you can see the springs just there that are bearing the weight of the car, and it will be the springs that will absorb the majority of the forces as the car goes over the bumpy road. So the stiffness of that spring will be very important. If you needed to support more weight, you would need the spring to be stiffer. So you want the suspension spring to be stiff enough that it can support the weight of the car, but you also need it to be not so stiff that it doesn't actually absorb the shock of the bumps as the car drives over it. So is there a way that the manufacturers could actually predict how stiff a spring is going to be? Well, of course, yes there is, and that's where something called the spring constant comes in. And that is where the why comes in, guys, in terms of what's the point in having this thing called the spring extension equation and something called a spring constant. Because anything that obeys what we call Hooke's law, i.e. the more force you put on, the bigger the extension, and those things need to be directly proportional for it to obey Hooke's law. As long as it does obey those rules, then we are able to predict how much that spring will either stretch or compress when you put force on it. And that's very important because that prediction allows us to decide what stiffness of spring to use in the suspension system of different cars, depending on how much weight they are going to need to carry. You'll hopefully be familiar with the required practical, guys, where you add more and more force to the spring and the spring extends proportionally with the force that you add each time. It's important to remember that it's the extension of the spring that we're interested in, not the length of the spring. So we're interested in how much longer the spring gets each time. And we know that that's a directly proportional relationship because when we draw a straight line, it goes through the origin. You can compare these two springs. Spring Y would be stiffer than spring X because with more force it extends to a lesser amount. So guys, we got to that point in the video where we have to look at another equation.
Look, you can't be serious, man. You cannot be serious!
Sorry about that, but it is important that we know these. So let's have a look at it. Of course, we find our equation here on the equation sheet that you will get in the physics exam. The force exerted on a spring is equal to the spring constant multiplied by the extension, or in other words, F equals K times X. So we can write out the word version of it here. Now the units for that, we know that force is in newtons, the spring constant is in newtons per metre, and extension must be in metres. So if it's not in metres, we have to convert it. So looking at this example here, we've got 2 newtons per metre as our spring constant, but you will see that our extension is in centimetres, which will mean that we have to convert it. We write the equation out, our spring constant is 2 newtons per metre, but we have to convert our 30 centimetres into metres, which we do by dividing by 100, giving us 0.3 metres, which we just put into the equation, and 2 times 0.3 gives us 0.6, and that is our answer. So that, of course, would be using the equation without changing it around. But what if we wanted to know the extension, as in this example here? Well, we know the force, we know the spring constant, but remember to rearrange an equation. If you move the thing at the beginning to the top and turn it into a triangle, we can then use the triangle. We cover up X, which is what we want, and we end up with the force divided by the spring constant, which we simply put into the equation, and that gives us our answer of 0.2 metres. So the question is, guys, would it be possible for me to actually calculate what the spring constant is for the springs in the suspension at the back of the car? Well, of course, yes, you can calculate it as long as you've got the other two pieces of information. So remember that the equation is force equals spring constant multiplied by extension. So as long as you know two of those things, you can find out the other. So all I need to do is measure how much the spring in the suspension at the back of the car changes its length, in this case gets shorter and is compressed, when I put a known weight, i.e. myself, onto the actual suspension. And I know that I weigh around about 85 kilograms, which would be 850 newtons of force. So let's try that and see if we can figure it out. So what I did, guys, I used a tape measure to measure how the length of the suspension spring changes when I stood and put my weight at the back corner of the car. And the spring actually moved by around about 2 centimeters. Okay guys, so putting those numbers into our equation, we need to rearrange it first, of course, to make K the subject of the equation, the spring constant. K is F over X, which is force divided by extension. The force is 850 newtons, my weight effectively, divided by 0.02 meters, which is centimeters converted to meters, of course. And our answer is here, 42,500 newtons per meter. So now we know about the spring extension equation, guys. We need to now think about what is actually happening when an elastic object changes its shape. Either it is extended or compressed as a result of a force on it. Okay, now that particular change in energy, guys, you are transferring energy to the elastic object when you put a force on it. And that elastic energy can actually be calculated, which is why there is another equation, that we also need to be able to use to calculate the amount of energy stored, the amount of elastic potential energy stored when an object is either stretched or compressed, and that would have to be an elastic object. So examples of elastic objects, guys, as well as springs, you've got elastic bands, bungee cords, the bow from a bow and arrow, and also catapults. And while we're talking about elastic as a definition, of course, you need to remember an elastic object is one that will change its shape when a force is put on it, but will return to its original shape once the force is taken away. So an inelastic object can still change its shape, but wouldn't necessarily go back to its original shape. So for example, if you stretched a piece of blue tack, it would stay the length that you'd stretched it to rather than pinging back to its original shape. So the blue tack would be inelastic, but springs and bungees such as this one are elastic. So in terms of the energy that we transfer to the elastic object, we need to have a look, I'm afraid, at another equation.
You're joking. Not another one? Oh, for God's sake, I can't stand this.
Okay guys, so not everyone likes equations, but the good news is we get all the equations we need on our equation sheet, and this is the particular one that we are talking about with regards to this example. The written equation looks like this. The energy transferred in any stretched object is equal to half of the spring constant multiplied by the extension squared. So you need to square the extension and half the spring constant and multiply them together. It can also be written like this. So remember, half times or 0.5 times is the same as saying half of. So you halve the spring constant and multiply it by the extension squared. You can, as I've mentioned before, rearrange the equation by putting the first thing at the top and making a triangle. So of course you'd need to remember that if you are finding x squared, then you would need to then get the square root of your answer in order to find what x was. And then of course if you were finding k, then you need to remember that your answer is half of k, therefore you'd have to multiply your answer by 2 to find out what k was. Okay guys, so I don't think I'm going to go into any detail on this video about how to actually use that equation or examples of questions, but I would recommend, if you're not sure, that you look up some videos on actually how to use it. I don't think you would be asked to rearrange the equation, but it is always worth using the formula triangles if you're not sure. Just an easier way of rearranging the equation. Probably not popular with maths teachers, if I'm honest, but certainly if you're not really a maths person, that is often the best and most straightforward way if you want to rearrange an equation. Okay guys, so that brings us to the end of another video. I just want to say thank you very much if you've stuck with it this far. It's a pretty warm day and it's getting quite hot in the car, so this is a good time to sign off. Thanks a lot for joining me, and I hope to see you again on Science Y. Hello everyone, and welcome back to Science Y, and thank you for joining me again. As you can see there, I'm out on the car. So is there a way that the manufacturers can actually work out how stiff the spring is going to be? So could it be possible for me to find out what the spring constant is for the... So might it be possible for me to find out what the spring constant is for the... Because remember, the equation is force equals spring extension multiplied... No, it's not.